Welcome you all to the analog and linear electronic circuit series. This is the last session for the unit first, that is single and multi-stage amplifier. So here is the outline of this session. We'll see the MOSFET linear amplifier, load line analysis, a small signal model, analysis of common source, common gate and common drain amplifier using the hybrid phi model, followed by the low frequency and high frequency response of the MOSFET amplifier. So let's start. So here is the MOSFET based amplifier. So it may contains the MOSFET and having the drain terminal is connected with the RD, where we are going to collect the V out, and we are going to supply the AC input signal which will amplify here. So we are going to give the AC inputs to the gate terminal. So this signal only will be amplified with this amplifier, and in our output will be collected through the drain end, and here source terminal is grounded. So now right side we can observe the characteristic for this amplifier. So the characteristic is showing the load line, and if we will solve load line characteristics, then we'll get the drain current and the GM. Basically, drain current for this saturation region can be written as like twice of K. K will be your mu cos W by L, where W and L are the dimensions, width and length of your channel here, and VGS minus VTN. VTN is the threshold voltage, means your MOSFET must turn on so that such that we will supply the sufficient gate voltage. Otherwise, if MOSFET will not turns on, then the operation will not be conducted. So with this manner, we can find out the drain current, that is ID, and GM, that is also can be find out the conductance, transconductance ID divided by VGS will be equal to the twice of K and VGS minus VT. So GM is an important parameter, so that we'll use during the AC analysis. That's why DC analysis is also important. Now, let's talk about a small signal equivalent circuit, means how our MOSFET will behave with a small signal, that is the AC type of the signals. So you can see the symbol for the MOSFET and the equivalent circuit, that is the AC equivalent circuit, which contains the gate terminal which is open because there will be the very high input impedance at the gate terminal, so the voltage will be simply VGS, whatever they will supply through the input, and the drain side the current will be the GM into VGS. It may also contains the R0 in parallel with this current source, and where R0 will be equal to the ID divided by VDS inverse. Now coming to the different types of the configuration, as we have already discussed the different types of the configuration for the BJT amplifier based. Now similarly here we are going to have the different types of the configuration. So first let's talk about the common source configuration. So here source is basically common to both, that is drain and the gate terminal. So here if you check the gate, we are supplying the input across the gate, that which will pass through the RSI followed by the R1, R2, it will be divided and will pass through the and we are going to collect the output at the drain terminal near to the RD. So again our objective is to find out the gain, that is V out by V in, also we can call it as the amplification gain. So with the help of the equivalent circuit, means first replace this configuration with the equivalent circuit. So below just see the equivalent circuit. Here if you will check, then this is very easy to draw the equivalent circuit, AC equivalent circuit. Like first replace this MOSFET with the VGS open circuited, then the current source of GM into VGS and R0 in parallel with them. Then RD parallel with R0, since we are going to collect the output across this, and input side R1 and R2 is in parallel, and RSI is in series with the current voltage source. So finally gain will be V out by V in equal to minus of GM R naught parallel to RD into RI divided by RI plus RSI. Similarly, here is the circuit for common gate configurations. So, and below the equivalent circuits, AC equivalent circuit for the common gate configurations. So again, if you will solve the V out and the V in, then you will get the voltage gain of GMRD parallel to RL divided by 1 plus GMRSI, and also we can find out the current gain. And now let's talk about the common drain, that is also called as the source follower amplifier. So again it have now your drain is common to both, that is gate and source, and we are going to collect the output across the source terminal. So that is why this is also called as the common drain, that is source follower. Now the equivalent circuit can be drawn. Now you just check it again. We are replacing the MOSFET with the same things, that is the VGS terminal, and with the gates, the source of current source of the GM VGS parallel with RS and R naught. RS will be parallel because now we are going to collect the output across the RS, and across the input terminal same R1 R2 are parallel and RSI in series. So our gain, that is the amplification factor, will be equal to V out by V in, will be equal to GM RS parallel R naught divided by 1 plus GM RS R naught into RI divided by RI plus RSI. So Vn you can find out with the help of the voltage divider rule, that will be equal to the Ri divided by Ri plus RSI. Now let's come to the frequency response analysis. So why is it important? Like BJT frequency response analysis we have already performed, where we checked that how the different frequency, the AC signals of the different frequency will behave with the BJT amplifier. So here again we'll check the how our AC signals will behave with the MOSFET based amplifier. So let's first check the about the lower frequency, the frequency which may have the frequency lesser than megahertz, means maybe in the range of the kilohertz, so that will called as the lower frequency. So first draw the equivalent circuits as usual corresponding to these amplifier circuits here, and find out the uh, cutoff frequency which can be obtained with the help of f is equal to 1 by twice pi of RC. So if you will find for unity gain frequency, then it will be equal to the GM divided by twice pi of CGS plus CGD. So CGS and CGD are in towards the input terminal. So with the help of this we can find out the cutoff frequency of the MOSFET amplifier. Similarly, for the higher frequency response, if you remember during the BJT response analysis, we have already studied what is the reason of this higher frequency response, because of the very high reactance of during the high frequencies. The reactance will be very low and capacitance will act as a short circuited. So in order to avoid these circumstances, the capacitance will induced at the different points. So that is also called as the Miller effect or the Miller capacitance. So because of the Miller capacitance, we have to find out the cutoff frequency, which will be different from the lower cutoff frequency. So how will we find out? So here first we have to find out the gain and the cutoff frequency. Again it will be similar to the 1 by twice pi of RC. So find out, we'll first solve, then we'll get the GM divided by twice pi of CGS plus CM. Cm will be nothing, this is equal to the CZD 1 plus GMRL. So this is also called as the Miller capacitance. Also it will be the Ft will be equal to the Gm divided by twice pi of Cg. So that's all in this unit. If you will check, then the MOSFET based amplifier frequency response, all these things are the very similar to the BJT based amplifier and the BJT, the frequency response of the BJT. So that's all in this unit, and you must try to solve some more questions based on these amplifier and the frequency response, all these. So I'm thinking, if time permits, we'll make a separate video for these numerical problems. So you must try to do the some exercises. You can check the Niemann books for these exercises. So in the next class we will see the unit second.